Rainhill, England, October 6, 1829. George Stephenson's locomotive sits on the track, a machine the establishment has already dismissed as too weak, too light, too fragile to compete. The canal barons and railway investors watch with satisfied smirks. But when the rocket begins to move, accelerating to speeds no one believed possible, those smirks vanish. This is the moment the old world ends and the modern age begins on steel rails. The tyranny of the horse. For 3,000 years, the mathematics of transportation had not changed. If you wanted to move something heavy, you needed muscle. Human muscle if you were poor, animal muscle if you had money. The equation was brutally simple and absolutely limiting. By the early 1800s, Britain had built an elaborate network of canals to move coal, iron, and manufactured goods. These waterways were engineering marvels, cutting through hills and spanning valleys with aqueducts that demonstrated British technical prowess. But they were also slow, expensive to maintain, and completely at the mercy of weather. When winter froze the canals, the economy froze with them. The canal companies had become rich, powerful monopolies. They set rates with impunity because they had no competition. If you wanted to move 10 tons of coal from Manchester to Liverpool, you paid what the Bridgewater Canal Company demanded, and you waited as long as they required. The journey took days, sometimes weeks. Some mines had experimented with another solution. Railways made of iron rails, along which horses could pull heavier loads than on dirt roads. The friction was lower, the mathematics were better. A single horse on rails could pull 5 times what it could pull on a road. But this was still animal power, still limited by biology, still trapped in the ancient equation. Here's what the establishment understood. Horses needed rest, food, and water. They got sick, they died. They could only work so many hours per day. These biological facts created an economic ceiling that no one questioned. Transportation capacity was fundamentally limited by how many horses you could afford to maintain. But there was a deeper problem the canal barons and railway investors refused to see. The Industrial Revolution was producing goods faster than horses could move them. Factories in Manchester were churning out cotton textiles at unprecedented rates. Coal mines were extracting fuel in quantities that would have been unimaginable a generation earlier. The production side of the economy had been mechanized, but the distribution side was still running on hay and hoofbeats. This mismatch was strangling British economic growth. Goods piled up in warehouses. Coal sat unmoved at pithead. The bottleneck wasn't production anymore, it was transportation. And the men who controlled transportation, the canal company directors and the railway investors committed to horsepower, had no incentive to solve the problem. They were making fortunes from the inefficiency. Into this world came a proposal that sounded insane to everyone who mattered. Build a railway between Liverpool and Manchester. But don't use horses, use steam locomotives, moving engines powered by coal-fired boilers that could run continuously without rest, without biological limits, without the fundamental constraints that had governed transportation since the invention of the wheel. The canal companies laughed, the railway investors were skeptical, the technical experts were certain it couldn't work. Steam locomotives were too heavy for the track, too slow to compete with horses, too unreliable to depend on for commercial service. Several had already been tried. Most had failed spectacularly, breaking rails, exploding boilers, or simply refusing to move under their own power. The consensus was clear. Horses had worked for 3,000 years. They would continue working. Anyone who thought otherwise was a dreamer, disconnected from practical reality. This was the world George Stephenson was about to destroy. The self-taught revolutionary. George Stephenson was born in 1781 in Wylam, Northumberland. His father maintained the stationary steam engines that pumped water out of coal mines, a job that paid barely enough to keep the family alive. Young George grew up in a 2-room cottage, surrounded by coal dust and the constant noise of mining operations. He was illiterate until age 18. There was no school, no books, no formal education of any kind. What he learned by watching the machines his father tended. While other boys played, Stephenson studied the beam engines, the pumps, the gearing systems. He took them apart in his mind, understanding intuitively how each component functioned within the larger mechanism. At 18, he taught himself to read so he could study technical drawings and engineering texts. At night, After 14-hour shifts in the mines, he would sit by candlelight, tracing his finger over diagrams, teaching himself mathematics, mechanics, and the principles of steam power. This was not genteel study. This was desperation. A miner's son had one way out of the pit: become an engineer. By 1812, Stephenson had worked his way up to engine wright at Killingworth Colliery. He was maintaining the stationary engines, just like his father. But he was also noticing something the educated engineers missed. The stationary engines were powerful. They could lift enormous loads of coal from deep underground. The energy they produced was tethered to a fixed location. What if that power could move? Stephenson began experimenting with locomotive designs in 1814. His first attempt, Blucher, was crude but functional. It could haul coal wagons at 4 miles per hour. The educated engineers called it a curiosity. The mine owners called it expensive, but Stephenson saw potential where others saw limitations. He spent the next 15 years refining the design, building locomotives for various collieries, learning from every failure. Each machine taught him something about weight distribution, traction, boiler efficiency. He was solving problems through iteration, through practical experience, through the accumulated wisdom of thousands of hours working with steam power. This gave Stephenson an advantage over the university-trained engineers who designed stationary engines. They knew theory, he knew machines, they calculated ideal performance. He understood what actually worked under brutal field conditions. They worried about elegance, he worried about function. By 1829, when the Liverpool and Manchester Railway announced a competition to select the best locomotive design, Stephenson had built dozens of engines. He had failed more times than most engineers had tried, and he had learned something profound. The problem wasn't steam power. The problem was generating enough steam to maintain continuous motion under load. This insight would prove decisive, because while the establishment was still debating whether locomotives could ever be practical, Stephenson was building a machine that would make the debate obsolete. The physics problem. The fundamental challenge of early locomotives was steam production. A steam engine works by boiling water to create pressure. That pressure pushes a piston. The piston turns a wheel. Simple in principle, brutally difficult in practice. Here's the equation that kept most engineers up at night. To produce useful power, you need high-pressure steam. To produce high-pressure steam, you need intense heat applied to a large surface area of water. To generate that heat, you need to burn fuel efficiently. Early locomotives failed on all 3 counts. The typical locomotive boiler of the 1820s was essentially a large metal barrel with a fire at one end and a chimney at the other. Water surrounded the fire tube. As the fire burned, heat transferred through the metal to boil the water. But this design had a fatal flaw. The surface area in contact with the hot gases was minimal. Most of the heat went straight up the chimney, wasted. This meant early locomotives needed enormous boilers to generate enough steam. Enormous boilers were heavy. Heavy locomotives broke the rails or required such strong track that construction costs became prohibitive. It was a vicious cycle. More power required more boiler required more track strength. More track strength meant higher costs. Higher costs meant the whole enterprise looked economically insane compared to horses. Most engineers accepted this as an unsolvable problem. They focused on making heavier, more robust locomotives that could survive the stress, even if they weren't economically viable. This is what the establishment expected to see at the Rainhill Trials: heavy, powerful machines that demonstrated technical capability even if they weren't practical. Stephenson looked at the same problem and saw a different solution. Don't make the boiler bigger, make it more efficient. Increase the surface area of metal in contact with hot gases without increasing the overall size of the boiler. This required rethinking the fundamental architecture. His breakthrough was the multi-tube boiler. Instead of one large fire tube running through the boiler, Stephenson designed 25 small tubes. The hot gases from the firebox passed through all of them simultaneously before exhausting through the chimney. This multiplied the surface area in contact with water by a factor of 25. The result was revolutionary. Far more steam production from a much smaller, lighter boiler. The mathematics were elegant. 25 tubes, each 3 inches in diameter, provided more than 13 times the heating surface of a single 9-inch tube. while weighing significantly less. More importantly, the water around the tubes boiled faster and more consistently, producing steam at a rate that earlier designs couldn't approach. But Stephenson didn't stop there. He recognized another inefficiency. The exhaust steam from the cylinders was simply vented to atmosphere. This was wasted energy. Stephenson redirected the exhaust up the chimney through a blast pipe. The high-velocity steam created a powerful draft, pulling air through the fire, intensifying combustion. The fire burned hotter. The boiler produced more steam. The engine ran faster. This created a feedback loop. The faster the engine ran, the more exhaust steam it produced. More exhaust steam created stronger draft. Stronger draft made the fire burn hotter. Hotter fire produced more steam. The engine essentially breathed, using its own motion to intensify the combustion that powered that motion. The establishment engineers thought this was absurd. Wasting steam to improve combustion seemed counterintuitive, inefficient, wasteful. But Stephenson understood something they didn't. The limiting factor wasn't steam pressure. It was heat production. By using waste steam to intensify the fire, he was converting useless exhaust into useful power. The final innovation was mechanical simplicity. Earlier locomotives used complex gearing systems to transfer power from the cylinders to the wheels. These gears were heavy, prone to failure, and absorbed energy. Stephenson designed a direct drive system. The cylinders connected straight to the driving wheels through connecting rods and coupling rods. No gears, no intermediate mechanisms, just pistons pushing wheels in the most direct way possible. This direct drive meant more of the engine's power reached the rails. It also meant fewer parts to break. Reliability increased, weight decreased, the machine became practical. The rocket that rolled onto the track at Rainhill in October 1829 embodied all these innovations. It weighed only 4.5 tons, absurdly light, compared to competitors that weighed 8 or 10 tons. The establishment looked at this lightweight machine and saw weakness. What they failed to see was efficiency concentrated into its purest form, the showdown at Rainhill. The Liverpool and Manchester Railway Company had a problem. They had raised enormous capital to build a railway line between the two cities. They had excavated cuttings, built bridges, and laid 40 miles of track. But they had no idea what should run on that track. The debate had raged for months. Some directors favored horses. Others wanted stationary engines positioned along the line, hauling trains via cables. A minority, led by company engineer George Stephenson, insisted that self-propelled locomotives were the answer. The board couldn't reach consensus, so they announced a competition, a public trial where any engineer could submit a locomotive design. The machine that best met the requirements would win £500 and secure the contract to power the railway. The requirements were specific and demanding. The locomotive must weigh no more than 6 tons. It must pull 3 times its own weight at 10 miles per hour. It must consume its own smoke to avoid polluting the atmosphere. And it must complete 70 miles, the equivalent of 10 round trips between Liverpool and Manchester, without mechanical failure. The prize attracted entries from across Britain. The most formidable competitor was Novelty, built by John Ericsson and John Braithwaite. Ericsson was a Swedish engineer with impressive credentials. Braithwaite was a respected London machinist. Their locomotive was beautiful, elegant, technically sophisticated. It featured a vertical boiler, copper tubes, and precision engineering that made it look more like a scientific instrument than a working machine. The establishment loved Novelty. It looked like what a locomotive should look like: refined, modern, clearly superior to the crude industrial machines that coal mines used. The betting favored Novelty overwhelmingly. Railway investors and canal company directors watched the preparations, confident that this elegant machine would prove locomotives could never compete with their established systems. Another competitor, Sans-Pareil, was built by Timothy Hackworth, an experienced engineer who had worked with Stephenson on earlier designs. Sans-Pareil was heavy, powerful, traditional. It represented the engineering consensus: more weight, more power, more reliability. Hackworth was certain that Stephenson's lightweight design would prove inadequate under real working conditions. The trials began on October 6, 1829. 10,000 spectators gathered along the tracks at Rainhill, drawn by the spectacle and the controversy. This wasn't just an engineering test. It was a referendum on the future of transportation. Would steam locomotives replace horses, or would this entire railway experiment prove to be an expensive mistake? Novelty ran. First, it accelerated smoothly, reaching 28 miles per hour in a demonstration run that drew gasps from the crowd. The speed was unprecedented. No horse-drawn vehicle had ever moved that fast. For a moment, it seemed Ericsson and Braithwaite had won decisively. But then the boiler began leaking. The elegant copper tubes couldn't withstand the pressure. The engine limped back to the starting point, trailing steam. Repairs took hours. When Novelty tried again, a pipe burst. The machine was withdrawn. Sans Pareil performed better. It completed several runs at acceptable speeds, demonstrating power and reliability. But it was heavy, slow, and its boiler efficiency was poor. It consumed vast quantities of coal and water. During one run, a cylinder cracked. Hackworth withdrew rather than risk catastrophic failure. Then came Rocket. Stephenson's machine didn't look impressive. It was small, simple, crude compared to Novelty's elegance. When it started moving, the spectators expected modest performance. What they witnessed instead was a machine that rewrote the rules of what steam power could achieve. Rocket accelerated smoothly to 29 miles per hour, faster than Novelty's best run. It maintained that speed for miles without strain. The multi-tube boiler produced steam so efficiently that the engine never labored, never struggled. It simply ran consistently hour after hour. When the trials extended over several days, Rocket performed every test without mechanical failure. The establishment watched in stunned silence. This wasn't supposed to happen. The lightweight machine, the one they had dismissed as too weak, was outperforming everything else by a margin that made competition meaningless. On the final day, October 14th, Rocket completed all 70 miles, hauling 3 times its own weight at an average speed exceeding 12 miles per hour. It won decisively. But the real shock came in what Rocket demonstrated beyond the trial requirements. During one demonstration run, carrying no load except passengers who had paid to ride, the engine reached 36 miles per hour. This was a speed no one had experienced before. No horse, no carriage, no existing transportation technology could approach it. The judges and spectators realized they weren't just watching an improved locomotive. They were witnessing the obsolescence of every competing transportation technology. The Liverpool and Manchester Railway Company awarded Stephenson the contract, but the decision was almost irrelevant. Word of Rocket's performance spread through Britain like a shockwave. Within weeks, Canal Company stock prices began falling. Railway proposals flooded Parliament. Engineers across Europe began copying Stephenson's multi-tube boiler design. The old world hadn't just lost a competition. It had been made obsolete in a single afternoon at Rainhill. The establishment crumbles. The Liverpool and Manchester Railway opened on September 15, 1830. It was meant to be a celebration. Dignitaries rode in decorated carriages pulled by Rocket's sister locomotives. The Duke of Wellington attended. Crowds lined the tracks to witness the first passenger railway service in the world. The day turned tragic when a passenger, William Huskisson, Member of Parliament, was struck and killed by a locomotive during a stop. But even this disaster couldn't obscure what the railway represented. For the first time, people could travel between 2 major cities faster than a galloping horse, in greater comfort and at lower cost. The implications were staggering. The economic impact was immediate and devastating to the old order. The journey from Liverpool to Manchester had taken 10 hours by canal. The railway cut that to 2.5 hours. Freight costs dropped by 2/3 almost overnight. Cotton manufacturers in Manchester could receive raw materials from Liverpool's docks and ship finished textiles back for export in a single day. The acceleration of commerce was unlike anything the Industrial Revolution had produced before. The canal companies panicked. The Bridgewater Canal, which had enjoyed a transportation monopoly for decades, watched its traffic collapse. By 1840, canal revenues had fallen by 50%. The company that had once dictated terms to all of northern England was begging Parliament for protective legislation. They didn't get it. The economics were too clear. Railways were faster, cheaper, more reliable. The canal era was over, but the broader implications reached far beyond canal company bankruptcy. The success of the Liverpool and Manchester line triggered what historians call railway mania. Between 1830 and 1850, Britain built over 6,000 miles of railway track. Thousands of miles more were proposed, approved, built, and opened for service in an explosion of construction that transformed the landscape. This wasn't just infrastructure development. It was a complete reorganization of British economic geography. Towns that were served by railways prospered, towns that weren't withered. The railway didn't just connect existing economic centers, it created new ones. Industrial development followed the tracks. Cities grew along railway junctions. The entire spatial structure of the British economy was rewritten in steel. The wealth generated was unprecedented. Railway companies became the largest employers in Britain. Fortunes were made in construction, land speculation, and equipment manufacturing. The stock market boomed on railway shares. The middle class expanded as engineers, managers, and skilled workers earned wages that previous generations couldn't imagine. But there was a deeper transformation happening that few contemporaries fully grasped. The railway was destroying distance as an economic factor. For thousands of years, transportation costs had been roughly proportional to distance. Moving goods 50 miles cost roughly twice what moving them 25 miles cost. This basic fact shaped settlement patterns, trade routes, and economic organization. The railway shattered this relationship. Once track was laid, moving goods 100 miles cost barely more than moving them 20 miles. The marginal cost of distance approached zero. This meant that factories could be located wherever coal and labor were cheapest, not wherever they were closest to markets. It meant agricultural products could be grown wherever soil was best, not wherever cities were nearest. It meant specialization could extend to national and eventually global scales. Britain's competitors watched this transformation with growing alarm. France, Germany, Belgium, and the United States all launched massive railway construction programs. But Britain had a head start. British engineers had experience. British manufacturers produced locomotives, rails, and equipment more efficiently than anyone else. And most importantly, Britain had George Stephenson. Stephenson didn't just invent the multi-tube boiler. He established the standard gauge, 4 feet 8.5 inches between rails, that became dominant worldwide. He trained a generation of engineers who spread across the globe building railways. His son Robert became one of the most famous engineers in the world, designing bridges and railways on 3 continents. The Stephenson family had created not just a technology, but an entire technological ecosystem that Britain could export, and export they did. British locomotive manufacturers shipped thousands of engines to Europe, Asia, Africa, and South America. British engineers supervised railway construction from India to Argentina. British capital financed railway companies from Australia to Canada. The railway became Britain's most valuable export, not because of the physical machines, but because of the complete system of knowledge, manufacturing, and expertise that British engineers could provide. The establishment that had laughed at rocket in 1829 found itself completely dependent on the technology they had dismissed. By mid-century, railway companies were among the most powerful institutions in Britain. They employed hundreds of thousands of workers. They influenced parliament. They shaped foreign policy. The canal barons had been replaced by railway barons, but the new elite had something the old elite never possessed: technology that scaled globally. The empire runs on rails. The transformation of Britain was dramatic. The transformation of the British Empire was revolutionary, because the railway didn't just connect Liverpool to Manchester, it connected London to Calcutta, Cairo to Cape Town, and Melbourne to Sydney. It turned a maritime empire into an integrated economic system controlled from a single capital. Consider India. Before railways, British control was tenuous, expensive, and limited to coastal regions. Moving troops inland required months. Moving goods required vast networks of animal transport that were slow, unreliable, and vulnerable to disruption. The British governed India more through local intermediaries than through direct control. The empire existed on maps, but its power was shallow. Railways changed this completely. The first Indian railway line opened in 1853, running 21 miles from Bombay to Thane. By 1929, India had 41,000 miles of track, one of the largest railway networks in the world. This wasn't just infrastructure. It was colonial control made physical. British troops could now be deployed anywhere in India within days. Rebellions could be suppressed before they spread. The Sepoy Mutiny of 1857, which nearly ended British rule, would have been impossible to contain without railways. The British learned that lesson. They built railways specifically to ensure they could move military forces faster than any rebellion could organize. But the economic impact was even more profound. Railways allowed Britain to extract resources from the Indian interior on an industrial scale. Cotton from central India could reach Bombay's docks in days rather than months. Tea from Assam could be shipped to Calcutta efficiently. Grain from Punjab could feed factory workers in Bengal. The railway integrated India into the global economy, but on terms that favored British industry. This pattern repeated across the empire. In Africa, British-built railways connected mineral deposits to coastal ports, diamonds from Kimberley, gold from Johannesburg, copper from northern Rhodesia, all flowed along rails to ships bound for London. The railways didn't develop African economies. They extracted African wealth. In Australia and Canada, railways opened vast interior regions for British settlement and agricultural development. The Canadian Pacific Railway, completed in 1885, connected British Columbia to Ontario, creating a transcontinental dominion. Without railways, Canada would likely have fragmented or been absorbed by the United States. The railway held the empire together physically and politically. The strategic implications were equally significant. A British merchant ship carrying goods from India to London could be threatened by pirates, storms, or hostile navies. But goods moving by rail from Calcutta to Bombay, then by ship to Suez, then by rail to Alexandria, then by ship to London, passed through British-controlled territory for most of the journey. The empire became a secure transportation corridor protected by British military power. This gave Britain economic advantages that seemed almost magical to contemporaries. British textile factories could receive raw cotton from India, manufacture finished cloth, and sell that cloth back to India, all cheaper than Indian artisans could produce cloth locally. This wasn't just superior manufacturing, it was superior logistics. The railway, combined with steam shipping, created transportation costs so low that distance ceased to matter economically. The impact on global power was decisive. In 1830, China was the world's largest economy. India was second. Britain was a distant third. By 1900, Britain was the wealthiest nation on Earth, controlling 1/4 of global GDP, despite having only 2% of global population. The railway, more than any other technology, created this reversal. Because while China and India had larger populations and often superior manufacturing traditions, they didn't have integrated transportation networks. Moving goods from interior China to coastal ports required weeks of human and animal labor. British goods, transported by rail to ports, loaded onto steamships, and delivered to Chinese markets, arrived faster and cheaper than Chinese goods produced locally. This wasn't fair competition. This was technological superiority weaponized as economic conquest. Other European powers recognized this and scrambled to build their own railway empires. France built railways in Indochina. Germany built railways in East Africa. Russia built the Trans-Siberian Railway, the longest in the world, to integrate its Asian territories. But Britain had the head start. Stephenson's designs, refined by his son Robert and thousands of British engineers, set the global standard. The modern world's economic geography was created in the 50 years after Rainhill. The great industrial cities, the major ports, the patterns of global trade, all were shaped by railway construction in the mid-19th century. We still live in the economic world the railway created. Even though trucks, planes, and container ships have replaced steam locomotives for most freight, the fundamental infrastructure of global commerce, the routes, the port cities, the industrial centers, were all determined by where Victorian engineers laid railway tracks. This is the hidden legacy of Rocket's victory at Rainhill. It wasn't just a better locomotive. It was the technology that allowed one small island nation to dominate the global economy for a century, and to establish an infrastructure of power that shapes international commerce even today. The modern world on tracks. Today, when you ride a high-speed train traveling at 200 miles per hour between Tokyo and Osaka, you are riding a direct descendant of Rocket. The technology is different. Electric power replaced steam. Welded steel rails replaced jointed iron. Computer control replaced human engineers. But the fundamental principle remains identical. A multi-tube heat exchanger, now called a turbine or electric motor, driving wheels directly through connecting rods, moving along steel rails at speeds that make road transport obsolete. The Shinkansen bullet train that began service in 1964 uses the standard gauge that Stephenson established. So does most of Europe's high-speed rail network. So do modern freight railways moving millions of tons of goods across continents. The decision Stephenson made in the 1820s, how far apart to space the rails, still governs how the modern world moves. But the deeper legacy is conceptual. Stephenson proved that solving transportation bottlenecks creates wealth, not just for the inventor, not just for the companies that exploit the technology, but for entire economies. The railway made Britain rich by moving goods and people faster. Modern logistics networks, from FedEx to Amazon, operate on the same principle. Speed of delivery creates value. Whoever can move goods fastest wins the market. The multi-tube boiler itself lives on in modified form. Modern power plants use the same principle. Increase surface area to maximize heat transfer. Jet engines are essentially multi-tube boilers that burn kerosene instead of coal. The internal combustion engine uses multiple cylinders firing in sequence to create continuous power, a direct echo of Stephenson's insight that continuous motion requires continuous energy generation. Even the resistance Stephenson faced from the establishment is instructive. The canal companies didn't fail because their infrastructure was poorly built or their management was incompetent. They failed because they were optimized for a world that no longer existed. They had invested in horses, boats, and water channels when the future required steam, steel, and rails. Their expertise became obsolete overnight. This pattern repeats in every technological revolution. Incumbents resist change not because they're stupid, but because change destroys the value of their existing investments. The railway threatened to make canals worthless. Electric power threatened to make gas lighting systems worthless. Digital photography threatened to make film manufacturing worthless. Incumbents always resist, they always lose, and they always look foolish in retrospect. What's remarkable about Stephenson is that he won despite having every disadvantage. He was self-taught in an era that valued formal education. He was from the working class in a society dominated by aristocrats. He was an engineer in a field controlled by investors and lawyers, and he built a machine that every expert predicted would fail. The fact that rockets succeeded wasn't just an engineering triumph, it was proof that practical knowledge beats credentialed ignorance when the stakes are high enough. The world we inhabit, the globalized, interconnected, rapidly moving civilization of the 21st century, began on October 14, 1829, when a small locomotive named Rocket completed 70 miles at 12 miles per hour, defeating heavier, more expensive, more elegant competitors. That victory established the template for modern logistics, modern economic geography, and modern global power.